Good morning, all. Today we are going to learn about serial communication protocols. This is the outline of this session. Initially, I will give an introduction to serial communications, and after I will move on to I2c protocol, and I will give an basic concept of I2c protocols. Later, I will give the complete working and design of the I2c protocol. Serial communication is a process of sending data one bit at a time sequentially over a communication channel. But in the case of parallel communication, we can send multiple bits of data simultaneously through multiple communication channels. And in comparison to parallel communication, serial communication offers a lot of advantages. These are the main advantages of serial communication. And it requires fewer interconnection cables because we are sending data in a serial manner. There is only few number of cables is needed for the communication, and there is no crosstalk also because the signal arrive at the devices at a different time, and there is no clock skew, so there is no synchronization difficulties will be there in the case of serial communication. And following are the main serial communication protocols: I2c, CAN, USB, SPI, Ethernet, etc. I2c stands for Inter-Integrated Circuits, and it is invented by Philips in 1982. And it is also called I2c or IIC. And it is used for communication between various integrated circuit. So it is called inter-integrated circuit. And it is a synchronous protocol. The synchronous means there will be one common clock which will be shared between various devices. And depending on the frequency of the clock, we can change, by varying the frequency of the clock, we can change the speed of the I2c transaction, and it is operating in multi-master multi-slave configuration. So there will be multiple master node and there will be multiple slave node can be present in the I2c system, and each master and slave nodes are identified by an address. And but in comparison to SPI protocol, the multiple slave devices are operated using a chip select or slave select input, but here it is identified by an address, and it is a packet switched network. So all the data are sent through the I2c bus is in the form of a packet containing some address field, some data field, and some control field, and it is a single-ended protocol. Since it is a single-ended protocol, there is only one data line or one data port is needed for communication, and it is also a serial communication. In comparison to other type of protocols such as SPI and UART, I2c protocol offers a lot of advantages. The main advantages of I2c protocol is it is very simple, because in I2c protocol, in order to establish a communication link between two devices, we only need two electrical wires. One is for carrying data and other is for carrying clock. And for any microcontroller, this input to these two wires can be emulated using a GPIO pin, using two GPIO pin. So there is no dedicated I2c hardware is needed for communication, and it is also a low cost communication protocol, and it also support multiple masters and multiple slave devices. and the selection between different slaves can be achieved using the address which is carried through the serial data line. And by changing the address in the serial data line, we can select the various slave devices. But in the case of SPI, we need one dedicated slave select line for selecting each slaves. And along with these advantages, the I2c has some disadvantages also. And the main disadvantages is it is a low speed communication method, and the size of the data frame is limited to 8-bit. Because it is a packet switched network, all the data is sent as a packet, and the data field of this packet is only 8-bit long. So we can at a time send 8-bit data at a time. These are the applications of I2c. The I2c can be used for variety of applications. For example, it can be used for I/O expander, switch or multiplexer, LED driver, temperature sensor, light sensor, battery monitor, memory, keypad monitor, pressure sensor, humidity sensor, radiation sensor, gas sensor, microcontroller unit, analog to digital converter, digital to analog converter, proximity sensor, accelerometer, touch screen sensor, pH meter, power supply controller, and more. Now let us see various characteristics of I2c protocol. The I2c has two bidirectional open collector or open drain lanes for data communication, and these lines can be represented as SDA and SCL, or serial data and serial clock. And the voltage level used for I2c protocol is either plus 5 volt or plus 3.3 volt. And we know that the I2c is a multi-master, multi-slave architecture. And for accessing various slave devices, I2c protocol uses a 7-bit address space, and rarely it uses 10-bit extension for the address. And if the I2c uses 7-bit address space, it can access up to 2⁷ devices or 128 devices. If the I2c uses 10-bit address, 10-bit extension, then it can access up to 2⁻10 or up to 1024 devices. And I2c support various speeds, and the starting speed is 10 kilobit per second, and it is this mode is called standard mode, and there is 400 kilobits per second speed, and it is called fast mode, and it also support 1 megabit per second, 3.4 megabits per second, and 5 megabits per second speeds. Let us see an example diagram of I2c architecture. Here in the diagram, we can see that there is one master device and 3 slave devices, and the master is wanted to communicate with these slave devices. And here in this diagram, we can see that the SDA lines of these slave devices and master is connected together. Similarly, the SCL line of master and slaves are connected together, and there is one pull-up resistor connected to the SDA line. Also, there is one pull-up resistor connected to the SCL line, and these pull-up resistors are attached to the VCC. And normally the value of this pull-up resistor is 4.7 kilo ohm for VCC equal to 5 volt. And if the VCC is 3.3 volt, then we took the pull-up resistor value as 3.3 kilo ohm. In the previous slide, I have said that the output pins of the
devices working in the I2c are in open collector or open drain configuration. And this open collector or open drain configuration dependent on whether the IC is made of TTL gates or CMOS gate. If the IC has a TTL logic, then the output will be in common collector configuration. And if the IC has a MOS or FET gate, CMOS or FET gate, then our output output will be in open drain configuration. Here in this devices is made by MOS CMOS. So here there are two MOSes, one MOSFET here and one MOSFET here, and the output will be taken at the drain terminal of this MOSFET. Here we can say that the SCL and SDA lines are connected to the drain terminal of this MOSFET, and this drain terminal is neither connected to logic high nor connected to logic 0. And for this both transistor it is kept open. It is not connected to logic high or logic 0. So the voltage at this point is undefined. So it is neither 0 or it won't be neither 0 nor logic 1. So it is undefined. But in order for the operation of the circuit, the voltage should be made either logic 1 or logic 0, and this is done using a pull-up resistor. Here we can see that there are two devices, device 1 and device 2, which is connected to the supply voltage through a pull-up resistor RP. Here there are two RPs, each for connecting, one for connecting serial data to the supply voltage and other for connecting serial clock line to the supply voltage. And this pull-up resistor is common for both devices. And if in this configuration, the voltage level at the SCL and SDA pin of both the devices should be a high voltage, because this pin is connected to the supply voltage through a resistor. And when in order to start a communication, the voltage at this pin should be bring down to 0. Suppose device 1 is a master device and device 2 is a slave device, and device 1 want to communicate with the device 2. So device 1 need to create a start condition, and in start condition the serial data line, initially the serial data line of the device 1 should be bring down to a 0 voltage. In order to achieve that, there is the data 1 out pin of this out transistor, SDA out transistor should be made high. In that cases, this output transistor will start conducting. So this output pin will connected to the ground voltage. So the voltage at SDA line will become 0. Similarly, after when the SDA becomes 0, the SCL line also should make 0. In order to do that, the gate voltage of the SCL output transistor output pin is make high. So the drain of this output transistor will start conducting. So the output voltage will be the voltage at the SCL point or voltage at the drain point of this transistor becomes 0. So it also start conducting and the SCL voltage also gets 0. And after start condition, we can achieve the communication similarly by modifying the gate voltage of each output transistors. I2c has two modes of operation. The first one is master mode and the second one is slave mode. In the I2c protocol, only master is capable of generating clock and initiating communication. So in the master mode, the master will generate the clock and initiate the communication with the slaves. And second mode is called slave mode. And in slave mode, slaves always check for the clock and data in the SCL and SDA lines. And if the slave find out that the address specified in the SDA line is same as the slave's address, then it will respond. So in the slave mode, we can say that in the slave mode, the slave node that receive the clock and respond when it is addressed by the master.
I2c is a packet switched network. It means that all the data communications happening in the I2c protocol is in the form of packets, and each packet contains some address field, some data field, and some control field. And this is an example of an I2c packet. This I2c packet start with a start condition and end with an end condition, or end with a stop condition. And we know that at the ideal state, I2c bus has both SDA and SCL lines are at a high voltage level. And when the master want to write or read from the slave devices, the master will bring down the SDA line voltage to a low value, followed by SCL line voltage to a low value. And this sequence indicate it is a start of a packet. After start condition, the master will write the 7-bit long address to the SDA line, and this address will select which devices it want to communicate, and followed by the address field it come read write bit. This read write bit specify whether the master want to read or master want to write from the slave device. If the read write bit is set to 1, it means that the master want to read from the slave devices. Or if the read write bit is set to 0, it means that master want to write to the slave devices. After read write bit, it comes acknowledgement bit. This acknowledgement bit is more like a handshake. If the acknowledgement bit is set to 0, it means that the receiver is acknowledged the transfer, and it is set to 1, it is not acknowledged the transfer. Followed by the acknowledgement bit, the 8-bit data frame is become 8-bit data frame. Here is the actual in this data frame the actual data is sent, and this data frame has only 8-bit long. So in order to send more than 8-bit data, we need to send it by send in the 8-bit duration. First 8-bit data, then acknowledgement bit, then 8-bit data, then acknowledgement bit, like that. And finally the stop condition. In the stop condition, the master will bring up the SCL line to a high voltage, followed by SDA line to a high voltage, and it indicates the end condition.
Now let us see the I2c data transmission operation in detail. Initially both SDA and SCL lines are high voltage. Here we can see that both SDA and SCL lines are high voltage. And after some time the only SDA lines are bring to low voltage. And after very few milliseconds later, the SCL line also bring to low voltage.
Here we can see there are 3 slave devices: slave 1, slave 2,
and slave 3. And suppose master want to communicate with the slave devices 3. So in order to communicate with the slave devices 3, it will use this slave devices 3 address. Similar to slave devices 3 address, there are specific address for slave devices 2 and slave device 1. But these three addresses are unique. So the master can easily identify slave 3 device with this address, and this address is 7-bit long. And in the case of slave 3, the address is 01010101. So master will place this address in the serial SDA line 1 bit after another. So initially it will place 0 here, then 1 here, then 0 here, then 1 here, then 1 here, then 0, then 1, like that. And after placing the 7-bit address, the master will set the read write bit. And if the read write bit is set, the master need to depending on the read write bit, master will whether read or write from the slave device. After sending the address, master will wait for response. And when the address is received, these 3 slaves will compare the received address with its internal address. Here slave 1 compare with the received address with the internal address, and during the comparison, slave 1 will find out that the address doesn't matches its internal address. And similarly, slave 2 also compare the received address with the internal address, and it also find out that slave 2 didn't matches the received address with the internal address. But in the case of slave 3, it is find out that slave 3 matches the received address with the internal address. So slave 3 understand that master want to communicate with the slave 3. So slave 3 will send a acknowledgement bit to master that it is received the address and it is ready for the communication. After receiving the acknowledgement bit, the master will start to send the data. Here the master will start to send the data to slave 3 through the SDA line. Here we can see that the master is sending the data through SDA line to the slave 3. And when slave 3 completely receive the 8-bit data, slave 3 send an acknowledgement bit to the master. Here we can see that slave 3 is sent a small acknowledgement bit to the master, and it indicates that slave 3 is completely received the 8-bit data. After completing the data transmission, the master will make the I2c bus to an ideal state, and this is done by initially making the clock line to a high value. Here we can see that the clock is set to a high value, followed by the data line SDA is set to a high value, and this is the end condition. This together to form an end condition. After end condition, we can see that the bus is gone to an ideal state. The ideal state of the I2c bus represented by both the SDA and SCL line kept at high voltage. And in this case, if some other master need to communicate, the other master can start the communication.